we can start.
Okay. Professor Murty, can we start?
Yes.
Okay. Okay. So good evening to all of you and welcome to this special webinar. And we are very delighted to have Professor Ramurthy of Queen's University amidst us today to speak to us on Ramanujan, the number theory, and the pandemic. I just want to share a few thoughts on this occasion, and then I will request my colleague and Dean of Homi Bhabha National Institute, Professor Nayak, to introduce the speaker. I've been a fan of many scientists in India, and Srinivasa Ramanujan is one of, I should say, the greatest luminaries whom we respect. He was a unique gift to the country, a child prodigy, a brilliant mind that could come up with ideas of far-reaching consequences with minimum formal training and in circumstances of poverty and an ambience that really did not appreciate his genius in the beginning phase. I came to know some of this through the reading of the book The Man Who Knew Infinity, which outlines very nicely his path from a struggling student to an internationally renowned mathematician. Of course, I also had the privilege of visiting his house at Kumbakonam where he had lived, and just one can appreciate the circumstances in which he would have become what he became later. Of course, one needs to have a knowledge base in mathematics, particularly number theory, in order to appreciate his seminal contributions. So I must say that in that connection, I am just a common person. But even as common persons, we still get to know his brilliance through many stories about him, like the mathematician Hardy visiting him in hospital, talking about the taxi cab number 1729 that sounded uninteresting to him, and we find instant response from Ramanujan that it's the smallest number that can be expressed as sum of two different cubes in two different ways. There is also a story that has been circulating widely and particularly in WhatsApp in the last week about Ramanujan's concept of friends through the numbers 220 and 284. Well, suffice it to say, I am not going to give a talk on this. In the words of Hardy, who was his mentor, he said, "I have never met his equal and can compare him only with Euler or Jacobi." And that speaks a lot about Ramanujan. Well, we know mathematics is central to development of all sciences. I read somewhere a very nice statement that mathematics is the language in which the pages of science are written. The constituent units of HBNI and our off-campus center at Bhubaneswar, they all deal with mathematics in some way. And we have, in fact, PhD programs in mathematical sciences in several of CIs. Of course, Professor Murty has been associated with IMSC. He is aware of the programs of IMSC. I thought that, therefore, it's very appropriate that HBNI organizes a program to commemorate the birthday of Ramanujan, which happened to be on 22nd, and also the death anniversary, not say death anniversary, death centenary this year. When I consulted Professor Arvind as to whom I could invite for this webinar and who could explain to some common persons like me the excitement in mathematics, his immediate suggestion was Professor Ramurthy from Queen's University. We are extremely fortunate to have you, sir, with us today, and I must express my gratitude to you for accepting our invitation at a very short notice of just a few days and agree to deliver this webinar at the risk of some inconvenience, because I know it is the time in Canada is now 8 a.m. and you are ready to deliver the talk to us. Thank you, Professor Ramurthy. And with this brief message, I would like to request my colleague, our Dean, Professor Nayak, to introduce the speaker. Then we go into the webinar. Professor Nayak, please.
Thanks, Professor Vasudev Rao. Good evening and welcome to HBNI webinar. First of all, I am thankful to Professor M. Ramurthy for accepting our invitations and to deliver a talk on Ramanujan, number theory, and the pandemic. In fact, most of these mathematicians who are joined today, they are quite familiar with the work done by Professor Ramurthy and his contributions in mathematical sciences, especially number theory. Professor Ramurthy received his PhD from the MIT, USA in 1980, and he is currently a Queen's Research Chair in Mathematics with a cross appointment in philosophy at Queen's University, Canada. He has many awards. The list is very long. He has been the winner of Queen's Research Prize and the Coexter James Prize, and as I told you, many other prizes in mathematical sciences. He is a fellow of a number of academic, fellow of Royal Society of Canada, fellow of National Academy of Science India, a fellow of the Indian National Science Academy, a fellow of the American Mathematics Society, and the fellow of the Canadian Mathematics Society. In philosophy, he has interest in Indian philosophy and in mathematical logic. Professor Ramurthy has published many articles, research papers. Out of that, 260 scientific papers in mathematics and 13 papers in philosophy. So you can see that he has contribution in both mathematics and in philosophy. And he has a large number of 14 books on various topics in mathematics. And I can see that 2 of them are directly connected with the Ramanujan's work. Professor Murty is widely respected as a mentor teacher, and he has supervised 49 theses. Without taking more time from you all, you may be eager to listen to such eminent mathematicians who is among us today to deliver a talk on Ramanujan, number theory, and the pandemic. Professor Ramurthy is requested to deliver his talk. Professor Ramurthy, Professor Ramurthy, please.
Okay, well, thank you.
Professor Ramurthy.
Should I start sharing the screen?
Yes.
Is that visible?
Yes.
Yes.
Okay, so first let me begin by thanking Professor Vasudev Rao for inviting me to speak on this occasion. Today, I mean, yesterday, I guess, or 2 days ago, was the birthday of Srinivasa Ramanujan, and it's a very important time for mathematics and perhaps the world as well. So the title of this talk is Ramanujan, Number Theory and the Pandemic. Let me first begin by getting the blessing. This is me receiving blessings from Ganesha at the Kanchipuram temple in Tamil Nadu. The title of the talk is Ramanujan, Number Theory and the Pandemic, and the question that arises is, how are the 3 topics of the title connected? Well, surprisingly, they are. The connection between Ramanujan and number theory is obvious, but what Ramanujan has to say about the pandemic is not so clear, and the purpose of this talk is to explain. Well, it turns out that Ramanujan had studied an important function now called the W function, which the pandemic. What is the W function? It turns out to be the inverse function goes to Z times e to the Z. Let me give you a crash course on mathematics and epidemiology. The idea of using mathematics to study the spread of disease goes back to Daniel Bernoulli. So here's a picture of Daniel Bernoulli, who in 1760 proposed a mathematical model to study smallpox. But the idea didn't quite catch on, pardon the pun, until the year 1902. It turns out that Ronald Ross begins the study of malaria in the year 1902. Interestingly enough, Ronald Ross was born in Almora, which is located in northern India, at the hills of the Himalayan mountains. So in 1902, Ross proposed a mathematical model to study the spread of malaria. He discovered that mosquitoes were the cause of transmission. Until his research, no one knew what the cause of malaria was. And he received the 1902 Nobel Prize in Medicine for his mathematical modeling of malaria. Later, he began training students. One of them was Hamer, and together with his student Hamer, Ross proposed what is now called the SI model for the mathematical study of diseases. The model may be familiar to many people in epidemiology. It's also the same, essentially the same as the predator and prey model. And the letter S stands for susceptible people, and I stands for the infected. So in this model, people would contract a disease. So there was no scope to model recovery in this early model. And this early model, 526. And in that model, they noted a system of differential equations that governs the growth of these quantities. Now, if you go to Calcutta and check where the laboratory in which Ronald Ross did his work, there's a nice plaque there. It says, in this laboratory, Surgeon Major Ronald Ross made the great discovery that malaria is conveyed by the bite of a mosquito. What I want to talk about is what's called the SIR model. So in 1927, Kermack and McKendrick proposed a more complicated model, now called the SIR model. Here the letter S and I are as before, susceptible people, infected people, but now R stands for recoveries, people to recover. There are three functions of time. These are three functions of time and are related by the following system of differential equations. ds of t is minus s of t I of t, di of t by dt is beta s of t I of t minus gamma t, dr of t by dt is gamma I of t. Let me try to explain what these are first. So beta is the recovery rate. So S of t counts the number of people who, and I of t is the number of people who are infected at time t. Obviously, if uninfected people come into infected people, the number of susceptible people will decrease. That's what explains the minus sign here. And then the beta is the infection rate. So this S of t is increasing, and that puts the minus sign there. And the number of recoveries should be increasing at a proportion of gamma I of t. And then the rate of change of infected people, of course, is the number of infected people minus the number of recoveries. So this is the very, very simple equation. You can explain equations to first-year undergraduate students. And the mathematics that I'm going to discuss in this talk is not the understanding of a first-year mathematics student, calculus student. So here are and McKendrick, and one could say that with this model, so let's try to solve the SIR equation. So let's go back and look at those equations. You will first realize that if you take the first equation and divide by the third equation, you can simplify the differential equation. See, the first equation is ds of t by dt is minus beta s of t I of t. And the third equation is dr of t by dt is gamma I of t. So if you divide the two, you will see the gammas cancel. And then you get a differential equation, which I will leave as an exercise. It turns out to be S of t equal to S of 0, which is the number of susceptible people at time 0 times e to the minus beta over gamma r of t. Now notice this beta over gamma appears, and that is a very important quantity studied by epidemiologists. Firstly, the number of people, the total population will denote by capital N, and we will assume that the population is not increasing with time t, the total population. So S of t plus I of t plus R of t will be equal to N. And if we insert this into the third equation, S of t plus I of t plus R of t is N, you can write I of t as N minus R of t minus S of t. And then S of t is given by this expression, therefore you shove it back in. You rewrite the third equation as dr by dt is gamma times capital N minus R of t minus S of t, but S of t is that, so you get this differential equation. And so this is the basic differential equation governing the behavior of the epidemic. Now, for the experts, there are, of course, more models, more elaborate models. You can bring in other parameters, but this is essentially the basic model. Now, you can't actually solve that system in a closed form using elementary functions. And Kermack and McKendrick kind of realized that. So what they tried to do was approximate the solution. So integral that appears, so if you try to integrate, you get dr by the integral of n minus r of t minus s of 0 times e to the minus r of t. So it's a transcendental function, and it's not an elementary integral. So Kermack and McKendrick were forced to approximate the exponential function by a quadratic function. So all of you know that e to the x is given by a power series, so you can try to approximate the exponential function by that power series. Now, as I mentioned to you in the earlier slide, beta over gamma is a very important quantity called R0, and it's called the basic reproduction ratio. And the fact is, if beta over gamma is strictly less than 1, there is no epidemic. It will die out. I mean, it will disappear. If beta over gamma is bigger than 1, you have an epidemic. And apparently, in March of this year, beta over gamma was close to 10 for the COVID-19. And that's why we have a global epidemic. So if you go back and look at this, the differential equation, dr by dt, becomes gamma times n minus r minus s of 0 e to the minus r0 times r. So that's the basic differential equation now. And because this function is a transcendental function and is not easy to integrate, Kermack and McKendrick approximate the exponential by a quadratic polynomial, and they look at this differential equation, which is not the same as this, but it's an approximation. And this particular one can actually be solved. So we use some first-year calculus. The integral is now more manageable. dr by dt is gamma times a plus br plus cr squared, where capital A is this constant n minus s of 0, capital P is r0 s of 0 minus 1, and capital C is r0 squared s of 0 over 2. So we have this particular thing, and all first-year calculus students know how to deal with that. It turns out to be the inverse of hyperbolic tangent function, which I will, of course, leave as an exercise. I'm not going to do that for you here. But students can try to do that. It's very simple. So you see now, by using an approximation, essentially first-year calculus, you already have some control of understanding of the epidemic. So, paper of Kermack and McKendrick, the novelty was that it modeled the spread of the disease via 3 differential equations and gave an approximate solution, which was then corroborated by actual events, and the error was not too large. For example, they were able to predict for any pandemic, there's a peak, and one can foretell when this will occur, provided you have proper information about the initial and exact information about the reproduction ratio. That's why the reproduction ratio, remember, is based on the number of people that are being infected, the number of recoveries. And so all these statistical parameters have to be gathered. And that's why you have to have accurate testing and so forth. So statistics plays an important role in collecting the initial parameters. And the final solution in their paper is that the number of recoveries at time t is given by this hyperbolic tangent function, and the number of infected people at time t is given by this square of the hyperbolic secant function. So all these parameters are clear, and by studying these functions, you can make very wonderful predictions. So this demonstrates the usefulness of mathematics in trying to control certain phenomena which to understand. So the function appearing in the above theorem, this particular function, is called the epidemic curve. It is a symmetrical bell-shaped curve that reflects what is often seen in epidemics, namely the cases continue to rise until they hit a certain peak point and then slowly reduce in number. It does not take into account variable rates of infection or removal. One can, for instance, reduce the rates of infection by following suggested guidelines of personal hygiene, mask wear, changing social behavior, as it were. Those parameters of social behavior are not inserted into the study of these differential equations. Clearly, in my opinion, pandemics are not tormenting the planet Earth for a long time. And a good example of this is if you just look at the Jain religion. The Jain religion is often advocated and mask wearing. And one can only surmise that this was probably motivated by various epidemics in the past. Now, because the Kermack-McKendrick model used a quadratic polynomial to approximate the exponential function, the question that arises is how big an error is it? And so this with Kumar and myself, so nobody seemed to have asked this question until this summer when Kumar and I took it up, and we managed to prove the theorem that the error is not very large. In fact, if you go back to the that they gave, you just need to add another constant phi prime, and the error of O of 1 over t. T, remember, is the time parameter. So the error with respect to time, and all that's needed is a small correction factor with a constant phi prime. So the Kermack-McKendrick solution, though it looks approximate, is not far from being the accurate solution, but it's not the exact solution. So that's the correction factor, phi prime plus O1. Now, the epidemiologists in the intervening years between 1927 to 1957 were thinking about errors, but they never did the calculation that Kumar and I did, but they were more preoccupied with exact solutions. So the person who was preoccupied with the exact solution is D.G. Kendall, and by defining a new transcendental integral. So his idea was, well, don't solve for R of t, and S of t, solve for time. So go in the other direction. So give time as a function of the recoveries, the infected people, and so on and so forth. So if you do it that way, then you can write the time parameter as an integral of the recovery function. Keep in mind that the rate of change of the recovery function was given by our earlier equation that I had outlined before. And this now brings in, if you think of it this way, time is given by this integral. And as you all know, this integral, the denominator of this integral has singularities. Those singularities turn out to be, there are two real singularities. Zeta 1 minus zeta 1 and zeta 2 turn out to be the unique negative and positive root denominator. Now, the fact that this has a unique real roots, one negative, one positive, is some basic calculus which you can do, but in Kendall's exact solution, these two roots of the denominator make an appearance. And the importance of those two roots will become clear in just a while. But let's point out here that what we're really interested in are solutions, roots of exponential equations. So instead of looking for roots of quadratic equations or cubic equations and so on and so forth, you're now looking at roots of this exponential equation. So here R0 is a factor, but you're looking for the root zeta in this equation. This is where the Lambert W function comes in. So this opens up a study of exponential equations. And if you the function that you need to study is y equals x e to the x. If you plot the curve y equals x e to the x, you get a curve like this shape, this nice shape. And it looks like the exponential function, but it's not. Remember, the exponential function is y equals e to the x. Here we have y equals x times e to the x. What's the difference, you may say? Oh, there's a lot of difference, and you'll see that in a second. The Lambert function is the inverse function of x e to the x. So if I was dealing with just the function e to the x, the inverse function is the logarithm function. But now the inverse function is this Lambert function. What is an inverse function? Well, the quick definition is, given a function f of x, we say g of x is an inverse function if f of g of x is x and g of f of x is x. That's the intuitive definition. Of course, the problem with the definition is that the domains and the ranges have to match up. You have to be careful with the domains and the ranges. So let's draw a little picture here. Supposing I have a set of 3 elements, a, b, c, and I have a range function 1, 2, 3, and I send a to 3, b to 1, and c to 2, then the inverse function goes in the other direction. So it'll send 1 to b, 2 to c, and 3 to a. That's now that's, of course, just a bunch of finite sets, but generally speaking, we're going to be looking at regions in the plane. So if I have an x, a blob of a region called x in the plane, and it goes to y, and then so the function f takes x into y, the inverse function will take y into x. But then, again, I told you that you have to worry about domains and ranges. Intuitively speaking, at least for the purpose of this talk, it suffices to understand the inverse function in the following way. Supposing I have a function f of x given by this red curve. If I draw the line y equals x, which is this line at 45-degree angle with the origin, and reflect that curve, the red curve, using that y equals x as a mirror, you will get the blue curve, this curve here, and that is the inverse function of f of x. In general, that definition kind of works. As long as you're dealing with real variables, I guess it's okay. But we will have to move away from real variables soon, but let me not get there just yet. So what is the Lambert function? So Lambert, 18th century mathematician, introduced this function in 1758 to solve trinomial equations. You know, the big thing in the 18th century mathematics was to solve equations, polynomial equations, try and find roots. We are all familiar with quadratic equations, x squared plus ax plus b equals 0. How to solve that quadratic equation, that's well known. It goes back to ancient India, ancient, Egypt as well, to some extent, ancient China. So in all of these ancient traditions, they knew how to solve the quadratic, and in some cases they even the 18th century mathematicians were trying to solve higher degree equations at the time, and Abel's theorem hadn't come around, but so here was Lambert trying to solve trinomial equations. And in that context, he comes up with this new function. So we're all familiar with the logarithm function. I told you about the inverse of x goes to e to the x, but the W function is the inverse of x goes to x e to the x. And if you look at that picture, y equals x e to the x that I drew in the earlier slide and reflect that picture in the line y equals x, you get this new function, which is the Lambert function. And you can see the Lambert function has two real branches. The first real branch is this part, and then in this tiny segment, it's got another piece here. So there are two, it's not univalued, so there are two branches of the, two real branches of the Lambert function. Now we come to an interesting theme of mathematics, which I call the game of the name. Naming things is an important part of the process of knowledge. And so this brings us to an essential aspect of the philosophy of mathematics. As you all know, the number system is built out of the discovery of zero, and giving nothing a name was a big deal. It was a big event in the history of civilization. Known evidence for the use of the modern decimal system goes back to India, and Indian temples dating back to 100 CE have the number system etched on their walls. The best known is the famous Vishnu temple in Gwalior, Madhya Pradesh, where on the temple wall, you can clearly see 270 written down. So this goes back, and the idea of thinking of naming nothing, it turns out to be very important. I hope all the microphones are muted. I can hear things on my thing. Okay, so the logarithm and the W function. We all logarithm. Being the inverse of the exponential function, it is possible to write down a power series expansion for the log function. So, for example, log 1 minus x, you all know power series for that. So there's a problem of analytic continuation of the logarithm, which requires a deep knowledge of complex analysis. So if you now start studying the logarithm function as a function of a complex variable, well, that forms an important factor of complex analysis. And a similar, and it looks like the first person who looked at this problem was Ramanujan. So Ramanujan rediscovered what is now called the Lagrange inversion formula. And so let me try to explain this. The general question Lagrange asks that if f of x is a given power series expansion, what is the power series inverse of x? And the answer by theorem, he answered this question. It looks like Ramanujan rediscovered it and applied it to determine the power series of the W function. So here's the Lagrange theorem. Suppose f of z is analytic. Don't need to worry about all the words in this theorem, okay? Suppose f of z is analytic, that is well behaved, in the neighborhood of 0, and f of 0 is 0 and f prime of 0 is not 0. Then f inverse is also analytic, and here's the formula, which I'll explain in a second. So don't worry about all these technical words, just ignore it. Let's just think of it in the following way. F of x is a power series. What is the power series? Well, the coefficient of z to the n in the power series of f inverse is the same as the coefficient of z to the n minus 1 of the power series of z to the n over n f of z to the power n. That's what Lagrange's inversion theorem says. Now let's just do a small mental exercise. Suppose we put f of z to be z times e to the z. What happens now? Well, z to the n cancels z to the n, and you get e to the minus nz, and it's very easy to figure out what the n minus 1 coefficient is of e to the minus nz. It's n to the n minus 1. It's exactly what Ramanujan does. So Ramanujan proves that the Lambert function can be given as a power series, and the power series expansion of the Lambert function is minus n to the power n minus 1 over n factorial z to the n. Now that's an amazing theorem. So this should be thought of, for those of you who are familiar with the power series of the log function, this should be thought of as the analog of that. But immediately you can check using first year calculus, there's a problem with this convergence. The power series only converges in a small circle, namely mod z less than 1 over e. So I'm giving you the reference to Ramanujan's collected papers. question 332 on, question 738 on page 332 asks for one to show that X equals this infinite power series. Ramanujan always had a nice way of rewriting his work. This result about the inverse expansion is really the same as this. This is more striking because for the uninitiated, it says X is equal to this horrible mess on the other side. So that's a kind of a way in which Ramanujan used to. And he posed this as a research problem, I believe, in the Journal of the Indian Math Society. Now, we've written W0 because, like the logarithm, the W function has many branches, and Ramanujan discovered only a part of the principal branch. So the question now, well, what are the branches of the W function? That's the first thing. First is analytic continuation, and the second is series expansions. And surprisingly, both of these problems were solved only recently, and that too partially. The continuation problem was solved in 1996 by Corliss, Gannett, Hare, Jeffrey, and Knuth. Now, some of you may recognize these names. These are all computer science people. And Knuth is, of course, famous for the discovery of tech that we all use. In fact, parts of this talk have been using tech. So it's the computer science people who really needed to have algorithms to compute W fast. And so they came up with these numerous branches, there are countably many branches for the Lambert function. And the power series expansion, that is extending the Ramanujan series so that it's valid for all values of Z, was solved only this year, April 2020. Bearden published a paper, there's a paper, in which he derived the principal branch that converges for Z satisfying, as long as Z is not into that, you have to, just like in the logarithm function, if you try to analytically continue the logarithm function, you have to cut off, a line segment in the complex plane. Usually it's the line from minus infinity to 0. You have to take that off, and then you can give a proper analytic continuation of the log function. Here, you have to cut off the line segment from minus infinity to minus 1 over e, which you can probably see that was coming if you had looked at the picture that I had indicated earlier, and there was a problem at minus 1 over e. And the series expansion that Bearden comes up with is that W0 is given by this infinite series, which converges now for all Z, as long as Z is in this region. And the A sub m looks awfully like Ramanujan's thing, but this term here, but there are these other binomial coefficients. So this is the expansion that Bearden comes up with. And I think he also indicates how one may derive similar series representations of the other branches. I think it'll be a nice research problem to actually come up with the explicit series for the other branches as well. Now let's go back to Kendall's exact solution and see what all this has to do with that pandemic. Kendall was trying to determine the peak of the pandemic, and in trying to do that, he realized that it reduces to determining roots of that exponential equation of the form a plus br plus e to the cr equals 0. Remember, a, b, and c were given in terms of those initial parameters. So now you can take this equation a plus br. Supposing I'm trying to solve this, you can rewrite this as a plus br times e to the minus cr equals minus 1. That's the nice thing about the exponential function. And now, usually, when you have e to the x equals y, you take logs of both sides and get x equals log y. Well, you do the same thing now. You rewrite this. You try to rewrite this as much as possible to make it look like you can take the Lambert function of both sides. And when you do that, lo and behold, you can find out that all the roots of this a plus br plus e to the cr equals 0 are given by minus a over b minus 1 over c w sub k of c over b e to the minus ac over b, where wk is the kth branch of the Lambert function. So in other words, all the roots are given in terms of the Lambert function. Now remember, in the Kendall paper, he was interested in the real roots because those real roots represented the number of deaths before the peak and the number of deaths after the peak. So only two of these roots are real, the others are non-real. The two real roots appear in Kendall's exact solution. They are, the positive root turns out to be zeta 2 equal to R0. Remember that R0 is the reproductive ratio. I of 0 is the number of infected people at time 0. By R0 plus 1 over R0, W0, that's the Lambert function, evaluated at minus e to the 1 minus R0 I of 0. So you can see how this reproductive ratio makes an appearance as an argument of the Lambert function, and this is the number of infected people after the peak, and the other ones before the peak is given by the other real branch, W minus 1 of the Lambert function evaluated. So these are the two things, and the total number of infected people in the entire epidemic is the sum of the two roots given by the Lambert function evaluated at e to the 1 minus R0 I0 and in both these branches. So that's basic. And so you can see here again the R0, if R0 is big, then we have epidemic. If R0 is small, we have things under control. So synopsis of events. So far, we've discussed the SIR model of the epidemic and the approximate solution given by the 1927 paper of Kermack and Kendall. And in 1956, Kendall is trying to give an exact solution, and the exact solution forces you to go and study the Lambert function. And then he relates the zeros of the function to the number of infected people before and after the peak of the pandemic. And in 1996 only, that's not that far back, Corliss and others give the analytic continuation of the W function and show the existence of countable number of branches similar to the log function. And in Ramanujan's second notebook, written in 1903, we find the rediscovery of the Lambert function and the development of the power series expansion for the real branch. And finally, in 2020, Bearden derives a power series expansion for WZ, valid for all Z in the principal branch. So some recent work with Kumar Murty, we look at special values of the Lambert function. They turn out to be arithmetically interesting. Being a number theorist, just as the logarithm function is very interesting for the theorist, the Lambert function seems to be very interesting also. Flash this for the experts. The idea here is that if you take alpha 1 to alpha n to be non-zero algebraic numbers, C1 to Cn rational numbers, then at least one of the following is true. C1 W alpha 1 plus Cn W alpha n is either 0 or transcendental. And W alpha 1 to the power C1 W alpha n to the power Cn is non-zero and transcendental. And the proof is not that hard. It just uses the Lindemann-Weierstrass theorem. But I put it in this fashion because for the experts, they may see resemblance to Baker's theory of linear forms and logarithms. And indeed, I believe that is the case. So this leads to some new transcendental numbers. So here's some nice corollaries of the study of the Lambert function. For any positive algebraic x, the integral from minus infinity to infinity, du by e to the minus u minus xu whole squared plus pi squared x squared is actually transcendental. It's actually a special value of the Lambert function. Now I'm putting this down like this is because this is exactly the way Ramanujan would write things down. He would have some brilliant theory up his sleeve and come up with some very interesting corollaries that any high school student can understand and then seduce you to study the theory by putting these tantalizing tidbits in front of you. I'm going to flash this one more thing for the experts. There's a famous conjecture in transcendental number theory called Chanuel's conjecture about linear independence of the exponential function. And if you apply Chanuel's conjecture, not a version of it, but the actual conjecture itself to the W function, you get that if alpha 1 to alpha n are algebraic numbers such that W alpha 1 to W alpha n are linearly independent over Q, then they're algebraically. That's an amazing, it's similar to the Baker theory. Log alpha 1, log alpha n, which are linearly independent over Q. They should be algebraically independent, but that's still not known. And what Baker proves is that they're linearly independent of Q bar. So something similar is happening with the W function. And the question then is, maybe the last implication can be proved using existing techniques. or some new developments in transcendental number theory. Now, I want to come back to Kendall because Kendall was preoccupied with getting exact solutions. So the question now is, how do you get the exact solution for the SIR model? The W function, no doubt about it. It leads to a power series expansion for the SIR model in the following way. So let me just give you a crash course in combinatorics. Supposing I have a series, f of z equals summation c sub n z to the n over n factorial. And I want to take e to the f of z. Well, e to the f of z is also going to be a power series. And the question is, what are the coefficients of z to the n over n factorial in e to the f of z? Well, they are given as polynomials, these Bell polynomials. And I will not get into it, but they're given as polynomials of C1 to Cn. And now if you go back to the fundamental equation that was at the heart of Kendall's analysis of the SIR model, he needed to study this exponential equation. Well, complex analysis tells you that this exponential function, this particular function on the left-hand side can be written as an infinite product, very much like a polynomial can be written as linear factors with roots. Similar to that, you have a nice factorization called the Hadamard factorization, 1 minus z over omega e to the z over omega, whereas omega is running over the zeros of a plus bz plus e to the cz. Now, in the earlier slides, we noted that all the zeros of such an exponential function, exponential polynomial rather, not an exponential function, exponential polynomial, can be given in terms of the Lambert function. So you now plug back into the, just basic mathematics. Now that you got the idea, you can see that your denominator in the Kendall integral can be written into the roots of that exponential polynomial. And lo and behold, the final answer of the Kendall solution is that the explicit formula for the SIR model can be written as a power series, and the coefficients are Bell polynomials in the roots given by the Lambert function. So let's discuss so far. The SIR model of epidemiology leads to a system of differential equations whose solution gives rise to a new transcendental function called the Lambert W function. Surprisingly, this function was studied by Ramanujan in 1903 as entries from his notebooks, both lost and found, show. And the study of this function from a complex analytic perspective and a number theory perspective opens us a new cosmos for us to explore. If we're able to see this far, it is because we are standing on the mountain peak of mathematics. Thank you very much.
Thank you, Professor Murty, for a very fascinating presentation, introducing us to the subject of epidemiology and its connection with mathematics and Ramanujan. There will be, I'm sure, questions from the audience. I hope you'll be able to spend another 5-10 minutes answering some of those questions.
Sure.
They'll be put on the chat mode, either in the WebEx or YouTube platforms. And maybe I would request my colleague, Professor Naik, to read out so that he can help you in looking at the questions. To start off, can I ask a question? That the recent pandemic has now, I should say, maybe 9 months old, and across the globe, several countries have been infected, and they have experienced this. So, how has been the experience in modeling this pandemic in different countries? And I'm sure there would have been variants in the model also, because it may not have been possible for the same approach to be used by different countries. So what is the experience on this is one question. The second question is it possible to look at this model introducing so-called waves, in the sense that in every country there have been situations that a peak is passed, it starts stabilizing, and then maybe some something is relaxed, some activity started, again the reproductive ratio probably changes from less than 1 and crosses 1 or whatever, and then it once again comes into another peak. This kind of additional implications of this have been looked at by any modeling method. This is my second question.
Yeah. So with respect to your first question, firstly, I'm not an epidemiologist. I'm not a mathematician.
Okay. Okay.
So before I answer the question with some sort of sense of authority, or semblance of authority, I better tell you that I'm basically a number theorist. What happened, why did I get interested in this work is because my brother Kumar, being the director of the Field Institute, was part of a task force for the Ontario government to advise the government on policy, basically from the scientific perspective. So he was a part of a panel, and then he knew that we both started realizing we had to learn epidemiology quickly to see what was going on, because many of these presentations didn't involve mathematics, but mostly statistical tables. So surely there was something deeper going on, and so we started working on this SIR model and came up with this small contribution, which essentially shows that the SIR model, the 1927 results of Kermack and McKendrick were not that far off. They were pretty accurate, and the error terms are not that big. So that was point number one. Point number two is that there are, to answer your second question, there are sophisticated modifications of the model that people have been looking at. For example, you don't make the infection rate as a constant. You make it as also a function of time. So beta of t and gamma of t, the recovery rate is a function of time. Beta of t, the infection rate is a function of time. So you now start introducing these parameters. And actually, people have looked at that, and there are lots and lots of papers. And some have proposed that beta of t is an oscillatory function, probably given by sines and cosines in terms of times and t's and cultural practices as well. Every time there's some festive season, for example, there will be more interactions. And every time there's no festive season, there will be fewer interactions. So it'll be a function of time. It may oscillate as a trigonometric function. And that kind of modeling has been looked at in the literature. So that's my understanding. And perhaps experts would know much more than that.
Okay. One of the participants has asked the question that you mentioned earlier during the year, first week of March, when the pandemic started spreading across. The beta to gamma ratio was of the order of 10. And
yes,
so he was asking, a person is asking, what kind of ratios are we seeing now?
Oh, I don't know. I'm sorry about that. I should have looked that up. The problem is, I don't know. But now with these new variants, it's frightening, isn't it?
Yes. Yes, it is. Another question is, to what extent the approximations introduced are valid in describing the pandemic?
Okay, so the SIR model is, you see, so in the summer when we started working on this, Kumar's original idea was that, look, the Kermack-McKendrick model used quadratic polynomial approximations. Maybe if you use higher degree approximations, you can explain the other features that they were noticing, that the peaks were going in different directions. And that's basically what motivated our study. And we were trying to show that if you used higher degree approximations, you should get better results. And the funny thing is, it's not true. You don't get better results. You keep getting a convergent number, and the error term is very small. So that's basically what we learned in the summer.
Okay.
With respect to modifications of the model, I have seen lots of papers where it gets more sophisticated, but the pure math doesn't.
Okay. Okay. There's an interesting question on how can you model or accommodate super spreader events. We know it has happened in our country, and I'm sure it has happened elsewhere, that a single gathering suddenly changes the entire situation by adding to the number of infections. So, how can that be incorporated in the model is a question.
Yeah, in some sense, I kind of answered that because I said beta, instead of thinking the infection ratio is a constant, it
Yes.
should be made as a function of time. And once you make beta as a function of time, it's going to, let's say at Christmas time, it'll be big. And at Thanksgiving or Diwali or whatever, it'll be big. So you could incorporate the super spreader gatherings as a function of time and look at beta and gamma as functions of time.
Okay, I will just handle one question which was put up by Professor B.V.R. Tata from the University of Hyderabad. He wants to know whether the definition of start and end time of the bell curve is space dependent. I not understood the question, but you may be able to appreciate.
Space dependent?
Yes, that's a question.
Somebody has a question. I think it's muted. Your thing is muted. Yes, go ahead.
Yeah. Is it okay? Yeah.
Yes. Yeah.
Because these bell curves are reported by each country, right? So I would call, so the country for Russia, China, the bell curve is already over. Whereas India, still the end of the bell curve is yet to come. So so it's country dependent, ultimately. That's why I call space dependent. But
okay,
what is the minimum window and what is the maximum window? When you say a pandemic is the entire pandemic, you also use that word.
Yeah. No, I don't know. So you're absolutely right. It's space dependent in the sense of, as I said, it's I think space is a wrong region. It's a function of the region and it's a function of time. Absolutely. Geographical region, sparsely populated areas are not, so you should really make the infection rate and the recovery rate as functions of the region and time. And so the more complicated the model gets with these extra functions of time, the more difficult it becomes to solve.
Okay.
I can't hear you. So I can't hear you. Your microphone is muted, I think.
I think there's some bandwidth issue, Professor Tata. Professor, yes, Professor Nayak can put the questions which have come across in YouTube.
Yes, sir. Professor Ramurthy, there are a few questions. One of the students is interested in doing the research on Ramanujan's work, further extension and other things. He would like to know how this scientific field is connected, except number theory. He want to know that Ramanujan's work, apart from number theory, how it is connected to other scientific fields.
Yeah, so that's a good question. So I only focused on the Lambert function, but Ramanujan did many other works, largely, of course, passionately driven by pure mathematics. But it turns out, you see, these divisions, pure mathematics, applied mathematics, and epidemiology, these are human divisions. I mean, nature doesn't know these divisions. And so it's not surprising that some pure mathematics all of a sudden finds applications in other areas. Now, most important, most impressive example I can, which seems to have quite an important relevance in the modern field, is his work on modular forms. Now, recently, there's been interest in studying what are called Ramanujan graphs. These are graphs which are not the XY graphs that I kind of drew in my talk, but rather graphs where there are vertices and then you draw edges if there's a connection. Those representations, these are discrete mass entities. And these graphs have been used to model, for example, the neural networks of the human brain. And if you think of neurons as vertices and synapses as the edges, the idea apparently, the way the brain builds its neural network of neurons and synapses is actually an expander graph. An expander, Ramanujan graphs are expander graphs. And so somehow into nature, there are these pure mathematical entities that have kind of been woven into the fabric of nature and that seem to arise. So it turns out that because somebody is in love with pure mathematics, they study these functions turn out to have applications later on. And so that's the most impressive example that I can give of Ramanujan's work to the real, so-called real world.
In fact, one of the students would like to work on epidemic modeling, and he would like to know what are the challenges in epidemic modeling, and do the models available today are adequate enough?
Yeah. Well, as I said at the very beginning, I'm not an expert on mathematical epidemiology. However, my sparse knowledge that I have learned in the last 6 months allows me to say that there's a lot of room for improvement. The problem with the epidemiological textbooks is that they're quite verbose. And in pure mathematics, we have a tendency to be terse, more, respect to equations and so on and so forth. So I think that a person who wants to look at it must look at it from a wider angle. And there is room for a lot of innovation because, as I mentioned in my small historical introduction, the use of mathematics for epidemiological studies is less than a century old. So there's obviously a lot of room for improvement. But in this process, you have to know your pure math very well, and you have to know your epidemiology also very well. So I would say you have to master pure mathematics, statistics, and mathematical biology.
Thank you, Professor Ramamurthy. And there are no more questions on the YouTube now. I am passing on to Professor P.R. Vasudeva Rao if there are more questions on WebEx.
Well, I do not find any more questions on WebEx, except there was a question from BBR Tata once again about the SIR model of deaths which you discussed. There were three differential equations. You mentioned death before and after the peaks, and he was unable to see the connection. I think BBR Tata is online. Maybe if you want to speak, you please unmute yourself and ask the question, please.
Because when you wrote the three equations and you put S plus I plus R is equal to N, and in the three equations, there is no death part considered. But when you talked about after a few slides, you say you started talking about deaths before and after the peak has achieved. Yeah, I lost the connection.
Okay, that's a very good point. Sorry to say this, but recovery is also it's a euphemism for death. So,
okay. So that is worried there.
The deaths are also included in the recovery. That's a bad way to recover.
Okay.
I think we will close now, but before closing, maybe I'll ask you a philosophical question, Professor Ramamurthy. We know that Professor Ramanujan was not really able to explain always how he was able to arrive at these conclusions. Many of them he was even trying to connect it to his religion. Or, people could not understand how did he come to these conclusions, and many more years of work had to be done. But what do you think is the situation now, and what more remains to be seen about Ramanujan's work? Is there some exciting question still pending?
Oh, definitely. I mean, if you look at these people who are talking about mock modular forms and his unfinished symphony, as it were, Ramanujan discovered a new world, which are generalized modular forms, which he didn't complete in his unfortunately short life. And so there's a lot of work to be done there. Does that answer your question?
Yes, yes, yes. So I think we do not have any further questions on the chat mode. I think many people have started thinking about the topics which you raised, and it was so much fascinating that it was.
More YouTube.
Yes. Is there a question?
Yes. One of the students would like to know, is not it possible to get the error of the model function from the complex root that can be available from the equation?
Yeah. So I had gone through that calculation very fast, but what I pointed out at the very end is the complex roots of the Lambert function will be entered into the Bell polynomials, and the Bell polynomials will give us the explicit solution for the SIR model. Okay, so that's how the complex roots enter into the SIR model.
I think we will stop here and convey our sincere thanks and gratitude to Professor Ramurthy. I can tell you, sir, that in the audience, probably more than 75% of the people were from other disciplines, chemistry, physics, engineering, biology, and so on. We were all together transported to a different world of mathematics thanks to you, and the connection between the mathematics as a subject and several other things like epidemiology. You made it very fascinating, and thanks you so much for joining us this morning at your time, quite early in the morning. But of course, you said that you are an early riser, sir. The 8 o'clock was not so early for you, but all the same, it's nice of you to spare so much time for us, and at short notice, you agreed for this lecture. Thank you once again, and thanks to everyone who has joined this program today. And for those who could not join, of course, this lecture will be available on the YouTube, and there is a channel HBNI webinar in YouTube where all the lectures are hosted. So people can look at it, or you can inform your friends who could not join to see this lecture later. I'm sure they will all be benefited. Thank you very much once again, and I think we can close the meeting at this point. Dr. Meena Mahajan, you want to add anything?
No, just clapping along.
Okay. Thank you. Thank you.
Okay. Well, thank you.
Thank you.
Hope to see you in India next